Welcome back to another Explainer brought to you by Forge College. Today, we're diving into the capstone project on modular smart contract design, and we are specifically zeroing in on integration testing and security checks. Now, if you've been following along in the Solidity from Zero track, you know exactly where we are. We're taking that theoretical blueprint we've been working on, and we're putting it through the ultimate stress test. It's that critical moment where we finally stop staring at individual, perfectly polished gears on a workbench, and we assemble the whole massive machine, plug it in, and, well, see if it purrs like a kitten or explodes into 1,000 pieces.
Okay, let's dive into this and lay out our blueprint index for today. First, we'll go from modules to systems, then setting up the sandbox, followed by orchestrating the flow. After that, we're injecting intentional chaos, doing some patching and reporting, and finally securing the blueprint.
All right, Section 1, from modules to systems, connecting the gears.
So, in our previous lesson, implementing core modules, we successfully built our individual gears, right? We had our registry, the AccessController, and the accounting contracts. But working in total isolation, well, that's a luxury we don't have anymore. Think about testing a single isolated gear. That's a unit test. It's safe, it's perfectly polished, totally predictable. But an integration test, that is the absolute chaos of snapping 3 modules together, turning the crank, and just hoping the teeth don't shear off. Unit tests prove your own internal logic works, sure, but integration tests, they prove your assumptions about the other modules work. And in Web3, let me tell you, incorrect assumptions will literally lead to drained treasuries. Moving right along to Section 2, setting up the sandbox for safe local testing. Let's move to and see how this builds. Because before we start stress testing this invention, we desperately need a safe local environment so we don't accidentally blow up the Ethereum mainnet. First up, we install Node.js and Hardhat. This gives us a lightning-fast, in-memory blockchain network just for iterative debugging. It's super quick. Second, we compile our core modules. And step 3, this is absolutely crucial. We create a simple text file, our debug_report.md template. When you're debugging multi-contract flows, your brain will play tricks on you, I promise. This logbook is basically what keeps us sane, tracking exactly what broke and exactly how we fixed it. Section 3, orchestrating the flow, the multi-contract dance. With our sandbox ready to go, it's finally time to run multi-step flows where our Web3 modules actually talk to each other. Imagine a user named Alice. Step 1, the system owner registers Alice. Step 2, they grant her permission. Step 3, Alice credits her account. Okay, so far so good, right? But then, step 4 hits, the owner revokes Alice's permission. And step 5, Alice tries to debit those funds anyway. If we built this right, the accounting module needs to check with the AccessController, realize she's been revoked, and just slam the door in her face. Honestly, we fully expect this final step to break during our first test run. And when it does break, not authorized is the exact revert string we want to see. Seriously, it's a beautiful thing. Seeing a transaction revert with exactly the right error message when a revoked user tries to steal digital ether, that's how we prove our cross-contract security is actually holding up under pressure. Because if Alice somehow managed to debit that account after her permissions were revoked, we'd have a catastrophic failure on our hands. Game over. On to Section 4, injecting intentional chaos to test for vulnerabilities. Now, what's really interesting about this slide is that this is where we take off our optimistic architect hat and we put on our malicious hacker hat to try and break our very own patent machine. This test planning matrix highlights the permutations of actors and call orders. Those first 2 scenarios, that's just the happy path and the revocation path we just talked about. But look at that third one down there, the reentrancy attempt. What happens if an attacker tries to trick our accounting module into processing a withdrawal multiple times before the module even realizes the balance is gone? Catching that requires some serious, intentional chaos. To stop that specific, nasty type of attack, we rely on the checks, effects, interactions pattern. It's a foundational rule of Solidity security. You can kind of think of it like a bouncer at a really exclusive club. First, you check, is this person actually on the guest list? Do they have a balance? Second, you apply the effects. You cross their name right off the list. You deduct their balance internally. Third, and strictly last, you interact. You hand over their coat, or in our case, you actually send the external token or ether. Because if you interact before you update your internal effect, digital goblins are going to create recursive loops and literally drain your contract dry. No way we're letting that happen. Section 5, patching and reporting, doing those test-driven fixes. And this brilliantly illustrates what happens next. When the machine inevitably catches fire in testing, and it will, we don't panic and rewrite the whole system. We apply minimal, test-driven patches to extinguish the flames. For instance, think about a bad accounting setup. The contract is just blindly trusting whoever is calling it, basically assuming whoever is knocking on the door is authorized. Yikes. But a good accounting setup. Before it does anything, it makes a strict call across the boundary to the access controller to explicitly verify permission. We are swapping out blind trust for authoritative verification. Every single time we apply one of those patches, we document it in our debug report. This document is absolutely vital. It holds the summary of the session, the test cases we ran, the exact failures we hit, the minimal fixes applied, and, crucially, any residual risks left over. This isn't just some boring to-do list, okay? It is the formal record tying our test failures directly to our architecture fixes. It proves our blueprint is actually evolving intelligently. And finally, Section 6, Securing the Blueprint, Building a Unified Secure Machine. So we've wired our isolated modules together, we've attacked them, patched the vulnerabilities, and documented the entire journey. Our modular smart contract system is finally acting as a patched, tested, and secure unified machine. So the crucial point is this: secure systems require explicit boundaries and rigorous state update ordering. By forcing our modules to ask for permission and strictly adhering to patterns like checks, effects, interactions, we massively reduce the surface area for bugs to hide. That is how you make a prototype scalable and enterprise-grade. But, a curious engineer is never entirely satisfied. I want to leave you with a provocative thought here. Even with brilliant integration tests, human imagination definitely has limits. So, what hidden edge cases did we miss that an automated fuzzer, like Echidna, which throws literally millions of random transactions at our code, might find? It's something to think about. To explore advanced fuzzing and to deploy this capstone project, be sure to visit forge.college. Keep building, keep testing, and I'll see you in the next explainer.